these things actually happen. So yes, thanks everybody for joining us on Zoom. The story is that the laptop connection in our classroom is all the way broken. No updates as to when it might be fixed. So for now, we are Zooming this week, and then we'll see what happens next week, whether I will be able to make that classroom work or whether we'll stay here for a while. But there are comprehensive exams in that classroom on Thursday anyway, which is why we can be here. So I have formative assessment number 3 for this class here. I went through this morning and read all your answers, and have some common points of things that I corrected on folks' answers that I wanted to go over. I also updated grades. A week from yesterday, your first individual analysis assignment is due, homework 3, I believe. How's that going? Reasonably well. I have office hours tomorrow if anybody wants to stop by and check on it. I tried to be as detailed in my rubric in terms of what I want as possible, but if you have any questions about what you should do or what should be included, please let me know. Otherwise, we can talk about fit and whatnot. So first question then on the formative assessment that we have to go through. In considering indices of global fit, what does the model chi-square tell you? So let's start with that one. So I can read your chats, I can listen to you, whatever you prefer. What does the model chi-square test tell you? First question.
How far off your model is from perfection.
That's right, how far off your model is from perfection. So in M plus and in R, Levon, what is perfection called? H1. Yes, that's the H1 model. Yes, indeed. And what is your model called? HO. I brought in a prop. So I went to Kohl's the other day to pick up an item that I ordered online. And I don't know if you've been to Kohl's lately with this new system, but they have like all these boxes, like little bins that are labeled with numbers, and you type in on your phone that you're here to pick something up and it tells you what number is yours. But just in case you can't read numbers, it prints out a little bit of your last name on the label. So I saved this to show you. Can you see this? Do you know what I thought when I saw this tag? I thought, I am the hoe. I am literally the hoe. Kohl's said so. So yes, this is my order. I am the hoe. My clothes and my model are not perfect, but we're making it work anyway. So the H1 is the perfect model. The HO is my model. So some of the fit indices, including the chi-square test of model fit, are comparing your model to perfection. So which ones are doing that besides the chi-square? Which ones are relative to perfection?
RMSA.
Yeah, RMSEA, root mean
RMSA.
square error of approximation, yes. And another acronym. There's one more, starts with an S.
SRMR.
SRMR. So the difference between those, SRMR is how far off you are in terms of correlations on average between what the perfect model is, the H1, and your model. RMSEA is offness per degree of freedom left. So all things equal, if you try to add stuff to your model to make it fit better, RMSEA is going to have a stricter penalty for adding things than the other measures of fit. But they're both relative to perfect fit, which is why, what is the best possible RMSEA or SRMR that you can have? 0. Yeah, meaning there is no difference between your model and perfect. So these ones that have the terms like error and residual in them, that means smaller is better because you want to minimize your errors or your residuals. So in contrast then, the other ones, CFI and TLI, what are they relative to instead?
The worst one?
The worst one. Yeah, they call it the null model, or sometimes it's called baseline. And the null model has all of the means in it and all of the variances in it. But the part that makes it null is no covariances whatsoever. So it's not really as null as it could be, but it's as null as we would entertain for the purposes of the measurement model. It doesn't work for growth models, for instance, when you're trying to recreate the means and variances, but it works for measurement models. So in that context, if we're starting with the worst possible model, then CFI and TLI is how much better is our model than the worst. And the best they can be, CFI tops out at 1. TLI, also known as NNFI, tops out above 1 because it doesn't have that boundary on it to make sure that it stays within a 0 to 1 range. So 1 functionally is the best that it can be. A few of you wrote down other things to keep in mind in terms of what affects your fit indices. So the reliability of your indicators also affects your fit, and the less reliable they are, the easier it is to fit. So if there's not a strong signal in terms of the correlation pattern, then alternative models can do a better job of capturing that weak signal, whereas if you have a really strong signal, then you have to get the model right to capture it. So that's one thing. Missing data is another. The extent to which you have missing data, then you lack the information to detect the misfit. How does power play into this? How about sample size? What happens to our model chi-square if we have let's go large sample first. Yeah, another way of saying it is that the chi-square will be very sensitive to deviations from perfection. So you will end up with likely a significant chi-square if you have a large sample just because you have a ton of power. So it's the same idea as having, significance starts to not matter at some point if you have a ton of power to detect tiny trivial differences, which is why the rationale is there for using these other fit indices. What if you have a small sample? What if you try to do a CFA on, 50 people or something? Could you do it? You could try. You can always try. You'll find out if you could do it. But in that case, you lack power to detect misfit. So then it's easier to say, look, my model's fine, because you don't have a lot of information to say that it's not fine with. So I've only seen non-significant chi-square for model fit a few times in my life. And it's usually for very small degrees of freedom left over. The more indicators you have, the harder it is to get decent fit, particularly with a very simple factor structure. Yeah, I think that's all I wanted to say about that. Any questions or points of discussion you want to raise about the first question?
So here, significant chi-square means bad thing?
Mm-hmm.
Okay.
It means you are worse than perfect.
Mm-hmm.
Yep. And there are no significance tests that go with CFI and TLI that would be commonly reported. There is one for RMSEA, but it's not a significance test of perfection. So there's a p-value that shows up next to RMSEA, and that is known as what? This was a homework question a couple weeks ago.
Interval?
There's a confidence interval, and then there's whether or not RMSEA overlaps a certain value. What is the name of that, or what is the value? Because it's a different standard than perfect. Yeah, close fits, yeah. So there's a chi-square test that goes with your model as the HO versus the perfect saturated H1. And then there's a test of close fit where you get a p-value for RMSEA as to whether or not it's different than 0.05. So 0.05 is a more lenient standard in terms of fit. It's close fit, not perfect fit. So that's another thing that people will commonly report. All right, others? So in your homework, when you're trying these models on your own data, you may very well come up with a model that some of the fit indices say is fine and others say is not fine. And in that case, I would hesitate to make a global decision. I would probably say something like, model fit was acceptable according to RMSEA, but not according to CFI, or something like that. You can just say, it meets the traditional cutoffs. Ideally, you would have given all your model fit results in a table or in a sentence, and so coming up with labels as to what is acceptable versus good versus excellent is, I think, less useful than just telling people what the numbers are, because then they can put their own verbal labels on what those numbers mean. All right, next up then. So describe the process of evaluating local misfit. What are we looking at? So how do we evaluate local misfit? Yeah, normalized residuals is the particular variant of it, but more generally, what are we looking for as evidence of local misfit? What do the normalized residuals tell us about? So residuals come in, you can get them in residuals for covariances, residuals for correlations, you can get them as normalized residuals, you can also get them as standardized residuals, which sounds like normalized, but it's a different denominator. And yes, the idea is discrepancy. So in that context, the name residual does not refer to residual error variance of the item. That is a different use of the same word. In this context of local misfit, it's discrepancy between what the data say in the H1 perfect model and what your model says, but going element by element. So for each predicted covariance between items, what's the right answer from the data, what's your model say? And a normalized residual puts that discrepancy between model and data into a z-score type metric, where the numerator is the size of the discrepancy, the denominator is the standard error of the covariance from the H1 model. And so relatively large values then tell you which covariances are being reproduced badly. So 0 would mean that you're spot on, you've nailed whatever the covariance is in the data. So if my standardized residual or normalized residual is positive, what does that tell me about those two items? Positive residuals.
The model is underestimating the observed covariance between those items?
Exactly. The model is underestimating their true relationship. They want to be more together than what the model says. So that means if it's negative, they want to be less together. Now, what you do about that is the tricky part.
Adding covariate?
Adding what?
Adding covariate between those two items?
Yeah, you could add an error covariance. So there were a few of you wrote down things like that. Keep in mind it's a covariance between the errors. It's not a covariance between the error variances. It's just a little bit of terminology there. So we're allowing the e's that are associated with one item to be related to the e's that are associated with another. That's one option. And if you look at the modification indices, otherwise known as cheat codes to me, they will tell you which modifications are going to help improve your chi-square and get it closer to good fit. The trick is that they will only tell you repairs that you can possibly make given your current model. So that means that if you have a single factor model, all your modification indices are going to be error covariances, because that's the only thing that it knows of to fix it. It will never be like, hey, I think you actually could use 3 factors, one for this item, one for these items, and one for the items that you started with. Like, it's never going to help you find a new model. So error covariances is one way to correct mispredicted relationships. What's another? What if you find like a clump of items that all want to be more together? Cross-loading is one. So if you have an item that wants to be related to items on a different factor, allowing that item to also have a factor loading on the second factor is one way to solve that problem. So if an item has loadings on 2 different places, that's called a cross-loading, by the way. And usually you would want to keep the item on the factor that you thought it measured and add a loading onto the other one. Where that solution can become problematic is down the line in terms of using the factors to predict other things or to be predicted. Because if you have 2 factors that are partially made up of the same stuff, and you want to talk about like, well, this factor predicts over and above this other factor. It's like, well, they're kind of the same. Like, how can you say that? So that's where cross-loadings get to be a little bit interpretationally problematic, is if they're based on the same information, it's hard to talk about the independent role of each factor. If I had a bunch of items that wanted to be more together, so in the example that I gave you with the forgiveness data, all of the positively worded items wanted positive error covariances between them. So I could have added those 3 error covariances, but I opted instead to make another factor. And so I'm choosing a model-based or sort of construct-based way of addressing that multidimensionality rather than just error covariances. In your projects, I'm not looking for necessarily a great fit. I'm looking for reasonable modifications. Okay, question, Ahmed?
Yeah, when can we decide that one of the items could be erased or eliminated from the scale?
The question was whether items can be erased from the scale.
Yeah, if the 2 items are highly correlated, so could we take away one of them?
If the loading itself is not practically significant or statistically significant, I would say then you could probably get rid of it. If you have an item that is correlated, like, 0.9 with another item, one might argue it's not adding enough new information, and items that have additional residual relationships with other items, sometimes you can clean up a whole model set of misfits by removing one item. That's problematic. However, keep in mind that in theory, you're lowering your reliability when you do that. So it's a trade-off between kicking out items to get good fit or to not have redundancy, but some redundancy is helpful in terms of precision. So for those of you watching or listening online, I'm making this gesture with my hands that doesn't really translate. I can't tell you what's a right answer. But what I can tell you, it's like if you have 10 items and you thought they fit a single factor model, but you have to add like 12 error covariances to make that fit, you do not have a single factor. You don't know what you have at that point. So I'm not looking like for that level of modification. But yeah, sometimes dropping an item is a reasonable thing, but it could potentially hurt reliability. Do you have an example you want to share with us from your data, or is this just hypothetical?
No, I just remember what we studied in IoT class, that the misfit people and misfit items is, so we have a room to erase some of the items if they don't fit the model well, or otherwise we can change the model. So I reflect this on CFA. So do we have this as well here?
I would say yes. However, the difference is in the size. Basically, how many items can you dump and still be okay? Like in an educational measurement context, you might have like 100 items trying to measure one thing. And if you complete a survey from the social sciences, you might have 5. So it's a much bigger deal to get rid of one of 5 than, to get rid of one and still have 99 left over. So I think that's the difference. And the other thing is that in educational measurement, the theta estimate or some linear transformation of it is a product, right, that you're going to put on a piece of paper and you're going to send to parents and stakeholders. Whereas in research, it's more like, well, I've found that extroversion predicts blah blah blah, and it's not about an individual person as much, and so you have a little more leeway because you're not making those kinds of very specific inferences. So. Yeah, I'm going to try to give everyone advice when I read your work, but I will tell you that if you had to add a whole bunch of error covariances, that's just a signal that there's something else there that probably needs to become a factor of some kind. What's reasonable to do and what's theoretically motivated, that's the dance, so to speak, between theory and methods and stats and art. But.
Yeah. By the way, is there something called person fit here in CFA?
That's not a thing in CFA. Person fit is not a thing. I have seen variations of something that's close to that as each person's individual contribution to the log likelihood. I've seen stuff with that to where they try to rescale it into some kind of like a leverage kind of idea, like if somebody is contributing more to the misfit than someone else. So the idea of person fit is also sort of predicated on a Roche model, where like this is the only choice. Like we don't have alternative models that we would test. Like this is your model, and if your data and people don't fit, you kick them out until you do. And that's a very different thing than this model doesn't work. Let's try a new one. Because kicking out people, unless, you have reason to believe that they didn't care or their responses aren't valid, like that's a level of forking decisions that can be difficult to justify.
Yeah. Thank you.
Thank you. Appreciate the discussion. So it's lonely on Zoom sometimes, talking into the nether here. So thank you for nodding and talking. I appreciate it. Yeah, so local misfit is the element by element discrepancy between what the model says and what the data says. How you remedy that sometimes means you need a different factor structure. Sometimes might mean that you need maybe one error covariance or two if they're justified based on content. But the more you have to mess with it, the more important replication is going to be.
Your action. Right? So, okay, so
Oh, maybe not talking to us. Okay. As we were. That's all right. Not only do I know how to unmute myself, I know how to mute other people as needed. It's an advanced Zoom skill right up there with putting a document in the chat window, which you can do, by the way, if you've configured that in your Zoom account. I find that super useful. All right, question 3 then. So I ended up writing like the same thing on everyone's response about this, omega and alpha. So what do they have in common first? What are they supposed to be telling us?
They both measures reliability.
Reliability for
Sum
a sum score. Under the assumption of a model, what would the reliability for the sum score be? They both assume unidimensionality. And so why this is less of a problem is because if you're doing omega, odds are good you just demonstrated you have unidimensionality. Otherwise, you'd have to go and make multiple omegas, one for each factor. So that's what they have in common. My problem with alpha is that a lot of people will just compute it, say it's good enough, and not explore the dimensionality because they think that alpha somehow makes that unnecessary, and that's not the case. So omega and alpha are both per factors. If you see like alpha for a total score, that doesn't make any sense. You will see that very, very commonly, but it doesn't make sense. Now, how do they differ from each other is the second part of the question. What does omega allow as part of its computation that alpha does not include? Yeah, 2 things. Unequal factor loadings, so items can vary in discrimination, and error covariances. So that was the one that I think a lot of folks forgot. It's not an assumption about error variance. So it's not a parallel items model. Each item can have a different amount of variance that's due to not the factor. Each item can have a different factor loading that quantifies how related it is to the factor. But omega has a spot in the denominator 2 times the sum of any error covariances. So what will happen is, like if you look at your one factor model and say, okay, well this fits okay enough, and if I add these 2 error covariances, it fits really well. Great. What's my reliability? Well, if you have positive error covariances, that's going to add to the denominator of omega without adding to the numerator. So it's going to sink your reliability because what's error is not independent anymore. So the covariances between the errors go into the denominator and they count against you. So you can have less reliability even though it fits better, because part of the information that's redundant is in the error part of the model, not the true score factor part of the model. So the error covariances is a big one because a lot of times we need those in practice to actually make this work. There are different kinds of omegas for multi-factor models, and you can read about those. I don't think I put any of those articles on your reading lists, but generally speaking, omega is per factor. So in your models, if you end up picking more than one factor, you would end up with an omega per factor, just like we did in example 4. Okay, any questions on that? Good. All right, link functions then, transitioning into this unit. What are logits and probits? What is the vocabulary word that goes with those terms? What are they? Link functions, yes, they are link or transformation functions. That is what they're called. So other ones that you may have heard of would be a log is a link function that's used for count type data where the top is unbounded but the bottom is bounded at 0. And log is another one. Trying to think of others that would apply. Those are the ones that I see most common. So logit and probit are link functions. So the logit, that was going to be my next question. What is a logit? It's the log of the odds of the probability of a 1, otherwise known as log odds. And what is a probit? Probit is normalized. Yes, it is. It's ogive. Yep, it's related to logit by a factor of 1.7. So probit is the idea of using the cumulative normal distribution and trying to figure out what the x-axis would be at that level of probability that's predicted as the conditional mean. So it's essentially a z-score. So the assumption of the scale has to do with the link transformed outcome. So they call that y star. So if you believe that y star is the continuous underlying variable of your binary response that has a logistic distribution, that's consistent with saying that y star has a residual variance of pi squared over 3.29. If you say, no, its pretend underlying distribution is normal, then y star has a variance of 1. And so that's why the 1.7 as the square root of that, approximately, it's actually 1.8, but 1.7 does a better job of converting. That they're on different scales. Since we don't know what the actual continuous distribution that underlies our binary response is, there's no way to say what's right or what's wrong. So they're just tricks. Probit is what you're stuck with if you use limited information estimation, which is something we haven't yet talked about, but we're heading that way. Logit or probit you have choices for if you are doing full information estimation. In both of them, what is neutral? So what is a logit or a probit that corresponds to a 50% probability? 0.5. 0. So that's the key. And if I know that my probability of answering a 1 corresponds to a logit, say, of 1.5, what is my probability of answering a 0 instead? Yeah, negative 1.5. So this is important for understanding what the hell your output means. This negative 1 times the value, because if your model is written as intercept slope, your intercept will tell you about the probability of a 1 for somebody with a factor score of 0. If your model is written as threshold slope, your threshold is an intercept times minus 1. It tells you about the probability of a 0 instead. So remembering that logits and probits are symmetric about 0, that you can multiply a value by minus 1 and get the other probability that you don't currently have, that allows you a great deal of flexibility in interpreting this stuff. And why do we need them? What purpose do logits and probits serve? And link functions more generally. Yeah, everybody wrote down something involving boundaries. The idea is that we can't predict the probability of a 1 or a 0 directly because a linear model would extend those predicted outcomes out of bounds. The link function makes sure that logits and probits keep going forever and ever, but when you back translate them into probability, then the probability stays bounded between 0 and 1. And if you're trying to write back translate or unlogit in a professional document, what words would you use instead?
Inversely?
Yeah, inverse link. Yeah, to go from logits back down to probabilities is an inverse link. To go from probabilities up to logits is the link. And which of the two has odds as part of it? Logits or probits? Yeah, only logits. So from logits, if you unlog it, if you exponentiate the logit, then you're in odds. Logit. Aye. And if you take it one step further, then you're in probability. There is no analog in probit. So probit requires integration to figure out what the probability is that goes with the z-score, or the table in the back of the book where people have worked out what it should be close enough. The good news is that when we get to ordinal data, which is starting next week, this all works the same way. The only difference is what is the model predicting as the 1 versus the 0, because in ordinal data there's going to be a series of them. All right, I think that's all of that. Any questions on any of those or things you want to talk about? So in the interest of doing something a little bit different, I want to jump into the example instead of doing more slides. Is that okay with folks? I'm kind of jumping ahead of some things, but I feel like we're at the point where numbers are going to help more than more words. So I have example 5, which I had posted last time we didn't start, but I have it up here. These are real data in example 5, which means that I can't give them to you. So inside the download packet is the syntax and output that goes with M+, as well as syntax and output that goes with R, but not the original data files, at least as far as I know. If I screwed up and put them in the folder, then please let me know. These real data come from a study of the oldest old, the octogenarian twin study of aging. So these are data from the baseline observation of people who were 80 to 100 to start with. And these are item response data related to instrumental activities of daily living. So it basically measures one's capacity to live independently. So this is sort of low-level abilities used for the purposes of screening folks to figure out who needs help. Most of this handout, I think, if not most but not all, is going to be in M+. I sat down to make this work in Lavon, and I spent about 45 minutes not getting the answers to match between Lavon and M+. And I'm like, why aren't they matching? I have Jonathan's code, I have his handout from the class 5 years ago, my results match his results, why don't they match M+? And then I noticed just a tiny little phrase that solved everything. It said, cases used. It did listwise deletion of incomplete responses in Lavon. Now, I don't know if this is a default that can be overridden, but I couldn't find it if it is. So I'm not reporting estimates from Lavon because I want to keep as much data in this analysis as possible, and not everybody answered every question. Odds are good if they didn't answer the question, that's indicative of something, meaning that missing at random is more plausible than missing completely at random. Did I try rm.na equals f? What does that mean?
So that's like, it depends on the function, but a lot of times that will say to keep the NAs and don't listwise delete them.
Okay, can you email me that, Nathan, please?
Yes.
And I will try it and see if that fixes it.
Okay.
But the reason that I didn't think it was possible is because I figured Jonathan would have already figured it out, and the fact that he didn't have it as an example I thought was noteworthy. So that means that when it comes time to do homework with these models, I will make sure that we have complete data and that the answers will match to the level of precision that I requested. But this is an incomplete data example. Whoops, yeah, see, I'm not going to remember any of that. So that's why if you can send me that text snippet and then point me to anything that demonstrates how to do it, I would greatly appreciate it. So this is me learning, continuing on my journey as a lifelong learner. You know, this morning I was thinking about this idea of fit as like relative to perfect is one standard and the worst is another. And I thought it's actually a useful thing to help with our self-concepts, right? So I was just at this conference. It's the Society of Multivariate Experimental Psychology. It's a group of quantitative psychologists, quantitative methodologists, and like everyone in the room is smarter and more accomplished than me, right? Like I'm just like this total imposter, you know, going to the show. And I could look at it that way, right? I could be like, yeah, this person knows more, this person's written more, this person's published more, this person has, you know, a bigger H index or whatever, and I could compare myself to perfect. But that doesn't help me. So I could instead compare myself to where I was. Like when I was a graduate student, I could barely make structural equation modeling code run. I had no idea what it meant. Like I was the epitome of dangerous. And the same thing with multi-level code. I could make some numbers come out, but I had no idea what they meant. So like if I look at that version of Lisa as like the null model, like I've come a long way relative to the null model. Am I at perfect yet? No, I'm not there yet. And I don't know that I ever will be, but thinking about these relative endpoints. So when it comes to using R, a year ago, I didn't even know how to open R. And now I'm all, oh, please email me that function. Like that's growth, right? So those of you who are learning things and feeling like you don't know enough or that you're not enough, we're not, right? It's a continual process, and we will always find things that we could learn more, do better, and just keep in mind the null model. Keep in mind 18-year-old you who didn't know any of this shit and how far you've come. The null model for the win. That's my public service announcement today. You feel me? I'm not even high on caffeine. I'm at 7-up level. I'm just feeling all philosophical. So yes. And yeah, faculty don't know anything either. We're all just trying to figure it out. That's the great irony, is that how I learned how to teach? Someone threw me in front of a classroom and said, good luck. So how'd I learn R? Good luck. You find other people's examples. So it's better than the yogurt analogy. Yeah, I don't make my own yogurt, so that analogy was not gonna
I
work.
think I was sleep deprived. There was something going on.
No,
with that.
I am the hoe. That's my only analogy right here. Cole said so. Did you miss this, Kaylin? Yeah, this is my receipt at Kohl's from picking up my online purchase, and I saw this name on my bag, and I thought, I am the hoe. That's me. Okay. Anyway, so thank you for that. I will keep working on my Levon to M+ translation. I also added something new to this handout that I hadn't put in before, which is the idea of a starting point. So no matter how many subjects you have, you can compute item remainder correlations, and you can compute Pearson correlations to get a sense of how related your items are. Well, you could do that for binary data, but it's not a great idea. So in this sample, I've got 7 items that we're going to be looking at, 2 different response versions, a binary version and an ordinal version. And each of these is whether or not you can do it, where 1 means you can do it and 0 means you can't. So I have the frequencies. 64% of the sample said they could do cleaning and laundry. 84% could make their bed. The hardest one then, what do you think the hardest item is, just looking at these figures right here? So this would be like your classical test theory indices of difficulty. Which of these tasks is relatively hardest? We have number 6 is 73%. That's actually sort of in the middle. Number 5.
Number 1.
Number 1. This one. So this one is the hardest in the sense of the fewest people got it right. Whether we want to call that high difficulty or low is confusing in the way that it's worded. What is the easiest one? What looks like the easiest thing that people can do?
7.
Yeah. So 94% of my sample said they could use the phone. And by the way, these data were collected in the 90s. They mean a landline. They mean getting up, walking over to where the phone is hanging on the wall, and making this sort of gesture with the dialing. So you can look it up on the internet, children, if you're not aware of what phones used to look like. But all right, just got a note in the chat. I will read that in just a second here since it's warm. But I do want to make a point that because most of the sample can do item 7, that item is going to be hard-pressed to show a relationship with other items. Because in order to have covariability, you need variability in the first place. So we're going to see a few indicators that this item is going to cause some estimation difficulties. So over here, I have a reminder of what the maximum correlation is for 2 binary items as a function of their means. And the maximum correlation of 1 for a Pearson correlation is only obtainable in theory if both items have a probability of 0.5 for their proportion of 1s. Otherwise, it's going to be this function that's going to be much less than 1. So what I have here are 2 different kinds of correlations for these 7 items. On the right-hand side here, where my cursor is currently, are Pearson correlations, just the regular kind. And on the left-hand side is something different known as a tetrachoric correlation. We haven't talked about this yet, but I'm deciding to go ahead and show you some numbers. So the first thing I want you to notice, how do these 2 sets of values compare? I have the color coding to help us. Vladimir, did you want to ask a question before I have people answer that question?
Yeah, sorry, but this is related to the previous thing. I have a question and a recommendation. First of all, in this case, so each case will have 7 possible values, right?
Yes.
From 0 to 7 eventually.
Each item is binary, so either they could not do it as 0 or they could as 1.
So, but if you sum these values, you will have something between 0 and 7, right?
Yes, they could.
Okay.
They could do all 7 as a maximum, or none.
That's the suggestion I need, because I've been talking with some friends, and when they conduct analysis and when they have this kind of data, they want to sum these values and perform some kind of linear regression.
Mm-hmm.
And I always try to explain why that's not a good idea, but in your words, do you have some main or primary reason to avoid that kind of analysis?
In this context, because they're binary items, there's no estimated error variance. So the only model parameter that we would worry about constraining equal are the loadings. And so summing these items assumes that this is a unidimensional trait and all items measure it equally well.
Yeah.
That's what I would say.
Completely agree, okay. Yeah,
and
thank you, Liz.
Both of those are testable assumptions. All right. Oh yes, correlations. That's where I was. So tetrachoric versus Pearson. What's your gut reaction looking at the size of these numbers? Green versus orange. Yes, they are on the same color coding scale.
Are you asking like which one's better, or how? Like what can we? I'm guessing tetrachoric is better.
They're quite different. Like if you just look at the size of these correlations, we've got between items 1 and 2, 0.9 versus 0.56. Like that's pretty different. If you look at the last row in particular, the correlation between items 1 and 7 is 0.28. The tetrachoric correlation is 0.68. So yeah, Pearson underestimates the relationships among these items. That's the bottom line. And items 1 and 7 in particular are a problem because item 7 is basically a constant. So item 7 is going to be limited in its ability to show a relationship with anything else because most of the responses are 1 for item 7. I also have down here the correlation standard errors that I got out of the software. And there's one that I wanted to highlight between item 4 and item 7 is way bigger than all of the others. The reason for that is shown in the bottom right here. This is a contingency table of responses between items 4 and 7. So there were 65% of the sample who said yes to item 4 and item 7. There was 29% of the sample that said yes to 7 but no to 4. Only 6% of the sample that couldn't do either, and there's nobody in this cell. So M+ throws a warning message about this particular cell and says that it's empty. And the reason is that everybody who said that they could shop, which is item 4, could also answer the phone. Now that makes sense, right? Like answering the phone is much easier. So it's like if you already are all the way up to doing your own shopping, odds are good you can get up to answer the phone. So this speaks to this idea of an underlying continuum of difficulty where this is a logical consequence of having items that are both relatively difficult and relatively easy, that you're going to have these empty cells. So in order for the limited information estimation to work, they actually have to add a tiny little number to make it not empty, to make it go. And what that tiny little number is going to differ across packages. But that's the only way that they were even able to estimate a tetraquark correlation, is to fill in some tiny value for that missing zero. So what is this thing, this tetraquark? Let me head over here to this part. So the idea of a tetraquark is using the proportion of responses in each of the 4 possible categories for a pair of binary items, and then figuring out what the underlying correlation would had to have been to create those areas. So in this little contingency table here, I've got areas A, B, C, and D, where people who can't do either are A, people who can do both are D, and then some kind of discrepancy would be C versus B. So think back to intro stat, when you first saw your very first scatter plot for like a Pearson correlation. What would a scatter plot look like for items that have no correlation whatsoever? This is a gesture question, or I'll accept words. Yeah, like a blob. Yeah, like a circle of blob, right? For a 0 correlation. And what would a perfect correlation look like in a scatter plot?
Straight line?
Yeah, some kind of straight line, depending on which way you're going, right? All the points on the line. And so somewhere between blob of 0 and straight line of 1, and if we cut up the quadrant of that scatter plot into 4 pieces based on the relative frequency of 0s and 1s marginally, then we can figure out what correlation is consistent with the amount of area in each. So if these 2 items were perfectly correlated, all of the area would be in A and D. None of the area would be in C and B. So the size of the offnesses is what this is using to try to figure out what the underlying correlation would have been. That's tetraquark. So you need more than just like the means, variances, and covariances of these variables to be able to compute it. This is something that has to be estimated. And I got it to estimate in M+, as well as in Levon. There are examples of those input files where in the download folder. So where I just basically fit the saturated model and asked for what the correlations would be to make this table. So the saturated model in limited information estimation is going to give you these correlations. Okay, so there's my public service announcement. Friends don't let friends report Pearson correlations for binary items. How's that? Deal? Same exact principle holds for ordinal items as well. There's just more than 2 cut points in terms of where the areas are. But to the extent that the areas are off of the line, then it's a correlation less than 1. So if I look at the tetraquarks, it looks like these items are fairly highly related. I don't see anything that jumps out at me as a negative relationship or 0 relationship, so I'm feeling pretty good about this just from staring at the data. Question, what happens if you calculate tetraquark correlation for non-binary continuous data? I'm trying to remember the right word. I think it's biserial. There's one that's a tetraquark and
Is it the
Pearson.
by point serial?
Yeah, there's point
Or something?
biserial and there's
Oh, yeah.
biserial. And I feel like
okay.
they're not synonyms, of course.
No.
That would be too easy. In the classical test theory set of slides, I think it's lecture 3, I have a page that has kinds of correlation. And yeah, okay, point biserial uses Pearson, so it's just biserial. And you'd have to look into the documentation for a program to see exactly what you get. I was able to figure this out by computing Pearson correlation by telling them that the items were just regular continuous and then making sure that it was different to get the tetraquarks. The only one that I can think of that wouldn't have a correlation that goes with it is nominal, because those are not ordered. So that wouldn't make sense to put on an X or Y axis, because you would have a series of binary items rather than a nominal response for that one. But these are fairly easy to get a hold of nowadays in terms of software, the tetraquarks are. Okay, any questions about the setup, the items, what we're doing here? Okay, so the code, you're gonna like this. I've got 2 models on the same screen here. Let me blow up the left hand side. So this is M plus code, which you are hopefully now familiar with. We tell it what the data are, we tell it what the names are, and the names of these variables start with a D for the dichotomous version. Could have been B, but I was feeling crazy that day. So IA for activities of instrumental activities of daily living. I put all 7 in the model. Here's the magical change. That line right there. Categorical R. There in Lavon, the call to Lavon, it's ordered equals, and it's the same principle. You tell it which outcomes are to be treated as categorical, and it figures out what the model needs to look like based on how many categories you have. So it will understand that I have binary data just from reading this in, or ordinal data, or a mix of binary and ordinal. It will understand, let's say that I have ordinal where it's 5 categories, but for this item people only answered 4 of the categories. It will know that. You don't have to tell it. So it's kind of beautiful. But this is the main thing that changes the type of model that you have from a standard CFA that has a linear effect of the factor loading on the expected response to an IRT/IFA where there's a nonlinear relationship, and we use a link function to predict the probability of a 1 instead of a 0. Let's see, make sure that you tell it what your missing data are, because otherwise it will count that as another choice in your answers, which you may not want. ID variable means that if you output thetas or anything else from the analysis, then it will add this column to your data set so that you can merge them in, so that's useful. In terms of the analysis options, I am in maximum likelihood using a logit link. So this is also known as marginal maximum likelihood. It's a term you may have heard in the IRT literature. It involves adaptive Gaussian quadrature to do the estimation, which is something we haven't talked about yet, so I'm just going to wave my hands and say it's the complicated one as opposed to the easier one. This is only a 1-factor model, so it's actually not too bad in this case. Once upon a time when I started building the homework system, I found out the hard way that people who were running M+ on a different version of Windows got different answers. So that was super fun. So I sent a note to the mutanes saying, how do I fix this? And this is what they told me. So this just tightens the convergence criteria so that it will be, I think, less susceptible to differences in precision across operating systems. So I'm throwing that into all of my examples. In output, I'm still asking for the standardized solution, although it's arguably less useful. And the analog to the residual command that gives you local misfit is tech10. What this output gives us is going to be every pair of item responses as a contingency table. It will say what the data say versus what the model says and come up with a whole series of chi-squares for how well each pair of responses has their relationship recreated. If you want to output factor scores, these are EAP estimates, so they are the most likely factor score for each person with some amount of error to it, and I'm asking it to save those factor scores to a data set with this name, and it automatically includes all of the item responses as part of the data set, and it uses characters, like a star, I think, for missing data, which if you try to read it into another package means it gets read into as a string variable, which is annoying. So this misflag option just changes that back into a missing data code so that it will be read in as numeric. And then pictures. So there's all kinds of pictures that we will get, such as information curves, theta distributions, and all that kind of stuff. And then the model, just this much. That's it. So IADL is the name of my factor. By says, hey, these are the items that measure it. So I have items 1 through 7 with a star after it, and you need the star here because the method of identification that I'm choosing is anchoring by persons, where I am fixing the mean and variance of the factor, my theta. The variance is fixed to 1, the mean is fixed to 0. That means I want to estimate all 7 loadings. And instead of intercepts, we have this thing right here, a little $sign. A dollar sign with a 1 after it refers to that item's first threshold. Binary items only have one threshold. Ordinal items have number of thresholds -1. So basically every transition between categories gets a separate threshold assigned to it. So this is saying I would like all 7 thresholds to be estimated, I would like all 7 loadings to be estimated, and I'm fixing the factor mean and variance for identification. This is consistent with my one-factor model. So other than a few additional estimation options, the code to set up the model is exactly the same, just with the dollar sign. Okay, how are we doing? Now the other side, the comparison model. The left-hand side is a 2PL model, 2-parameter logistic. The right-hand side is a 1PL model, otherwise known as a Roche model. And the difference between them is right here. That's it. I put the word loading in parentheses. That label is functioning as a constraint that is going to make all 7 loadings be the same number. So the 1PL, the one parameter that the 1 is counting, is location, which is operationalized as a threshold in these models. All of the loadings are being held equal, and I'm asking it to find one number that holds for all 7. I still have to estimate the loading because I have factor variance fixed to 1. Alternatively, I could have set all of the loadings, fixed them to 1, and estimated the factor variance instead. That's the other way of identifying the model. Otherwise, all the rest of the options are the same, although I probably should have changed this to be 1P in that case rather than 2P. So my bad for that copy and paste error. So it's not so bad. By the way, today I'm going to have to go around 3:10 because I got a faculty meeting that was scheduled for 3:15. So I'll hang in there for like 8 minutes. Can we do it? We'll see the numbers. So here's the results of both models. 2PL on the left, 1PL on the right. I am the hoe, so that's good news. So my log likelihood for my one-factor binary model with all the loadings separate is -1454. Is that good? What would I compare it to? H1. Do you see anything on this page that says H1? Nope. It's gone. Say goodbye to global model fit. It's gone. I get AIC and BIC, so I can do relative model comparisons. I can also compare the log likelihood from a model where all the loadings are separate to the version where they're all the same. And I get this extra stuff here where I've read on discussion boards by the creators and other people that if these don't match at all, then you shouldn't use them. And they don't. And that's it. So we don't have a perfect model as a comparison anymore. The reason is that if we're not willing to assume our data have a multivariate normal distribution, then we can't just keep track of their means, variances, and covariances and call it good. For categorical data, the higher moments are also relevant. So what these chi-squares are trying to refer to is a 7-way contingency table of all possible combinations of zeros and ones across the items. So the degrees of freedom, where the 113 comes from this chi-square, is how many possible cells there are, which is 2 to the 7th. So 2 for each item being binary to the power of 7 is 128, minus the 7 loadings we estimated, minus the 7 thresholds we estimated, minus 1, because that's the last degree of freedom to fill out the rest of the table. That's where the 113 comes from. So it's trying to assess fit of a 7-way contingency table of the data versus what the model says. So back when you first learned about chi-square and significance testing with chi-square, do you remember a caution about small cells and chi-squares? Like you need to have at least 5 people per cell for this thing to be believable. So that means that we would need to have at least 5 times 128 people to fill out all the cells and have a shot at this being reasonable. And it's telling us with the error messages that some of the cells were not observed, and so we can't do that. So this method of assessing fit is not going to help us do much at all. So absolute fit is temporarily gone. It will come back probably on Thursday. But we can do relative fit. So we have -2 times the difference in log likelihood between our two models is about 20 on 6 degrees of freedom. So where did that come from? What are my 6 if I'm comparing the two models on the left and the right of this example?
The 6-factor loadings, the 2PL model?
That's it. So the 2PL model has 7 factor loadings. The 1PL model has 1 for a savings of 6. So the fact that this p-value is significant means constraining the loadings made my model ... You got 4 choices here. Worse, not worse, better, not better. The fact that this significance test this test is significant, likelihood ratio test means what? Which is better? Yeah, significance test means one of them is better. So it's better or not better. Yeah, the 2PL. So you can think of it either way. You can say that if I start with a 1PL and I add 6 loadings, it's significantly better. Or I can think of it as if I start with a 2PL and I try to simplify, it's significantly worse. So this is evidence that a Roche model / a sum score of these 7 responses is not appropriate. The items differ in their discrimination. We would typically not do any kind of constraint on the thresholds, though, as location parameters. Okay, how are we doing? So all of this lack of fit stuff is a consequence of using full information maximum likelihood as our estimator. The multi-way contingency table is a difficult thing to try to recreate, and we don't have enough data to do it in most cases. So that's why limited information estimation is often used instead, which is based on starting with the tetrachoric correlations and fitting a CFA model to them, essentially. So we start with the summary of the item responses, then fit the model to that summary. That's limited information. And because we have a covariance matrix to come back to, we got H1, we got fit, we got everything coming right back. So the end of this handout, I'll show you what that looks like, but it will look quite similar to what we had before, which is why people call this CFA for categorical items. So then foreshadowing what we get to dive into next time. I only have the output from the 2PL model, given that the 1PL did not work as well. So there's 3 different sets of numbers here. There's unstandardized model results, which give me factor loadings and thresholds. So you know what a factor loading is, right? Yes, you do. It's the same thing it was a month ago, or 2 months ago at this point. A loading is a slope. It's the change in y for a 1-unit change in x. So in this case, x is the factor, the trait, theta. The expected item response is in logits. So these slopes tell us the change in the logit of y equals 1 per 1-unit increase in theta, which is a standard deviation increase given that theta has a variance of 1. So the reason that these numbers look so dang big is they're in logits. That's why they're kind of crazy. Then we have this threshold thing, which is conceptually backwards. We'll spend more time on that later. Then we have our standardized results, which have standardized factor loadings, and these you can think of in the same way as standardized factor loadings in CFA. in that this is the correlation between the item response in logits and the latent trait. And then we have over here on this side the IRT version of the same information. So these are discriminations, which are the exact same thing as loadings if your factor variance is 1. And these are B difficulties instead of either thresholds or intercepts. So I've got 3 different sets of numbers here that I have to try and work through, and that will be our task for next time. All right, questions before we call it a day?
Lisa, can I ask a clarification question
Please.
on interpretation of the 2PL versus 1PL?
Let me go back
You
up to
said
that.
constraining the loadings made the 2PL significantly worse.
I would say it the other way. So if you're starting with 2PL and saying, could I get away with constraining the loadings? No, constraining the loadings fit significantly worse. If you are starting with 1PL and say, is it going to be better if I let them be differently discriminating? Then yes, it's significantly better.
Oh, I see. Thank you.
Yeah, it depends on the point you're trying to make with the comparison. Like usually if it's me and it's like, yes, reviewer 3, we looked at a Roche model, it didn't fit as well, moving along, like that is a worse, like I made it worse by constraining. Whereas if you're a Roche person and you're testing the Roche assumptions, then it would phrase it the opposite way, that 2PL fit better.
Okay, thank you.
And AIC and BIC would provide converging evidence in theory too. All right, other clarifications or questions? All right, then thank you for being here. I will see you on Zoom again on Thursday, and I'll let you know what happens about next week. So have fun working on your data analyses. Let me know if you need anything. All right, bye, folks.